Usually when we think about the ultimate end of the universe, our minds immediately go to something loud.
Oh, yeah, absolutely.
Like we're practically conditioned to expect this massive spectacle.
Right.
A huge galactic collision or a supermassive black hole just devouring a star system or a star going supernova.
Right, something explosive.
Exactly. We anticipate this violent physical event with matter just crashing into matter. But today we're looking at something entirely different.
It's actually completely counterintuitive to look for destruction in the absence of things.
Yeah.
But physics rarely cares about human intuition, as we know. And a profound paradigm shift is happening in cosmology right now.
A really profound one.
It forces us to look away from the bright, glowing objects that we've spent centuries studying, and instead we have to look directly into the pitch-black shadows.
And that is exactly our mission for today's deep dive. We're unpacking a fascinating stack of recent research surrounding NASA's James Webb Space Telescope.
Some really incredible data coming from that telescope.
Unbelievable stuff. And our goal today for you listening is to understand a reality that sounds almost paradoxical, really. We're going to look at how massive, invisible pockets of completely empty space are actively tearing the fabric of the universe apart.
It's a topic that demands we rethink our fundamental understanding of space-time. I mean, we are looking at forces that are entirely invisible.
Totally invisible.
Yet they possess the power to dictate the geometric fate of the entire cosmos.
So if you are the kind of listener who loves an existential aha moment, you are in the exact right place today.
Definitely.
We are going to explore the mechanics behind these cosmic mysteries. But before we can get into how nothingness is destroying the universe, we have to establish the geometry of the battleground, right?
Yes, we need to picture what the universe actually looks like on a macro scale.
Right. And if you follow astronomy at all, you already know the universe isn't just some random scattering of stars. Matter clusters together. Gravity pulls galaxies into these massive interconnected filaments.
What we call the cosmic web.
The cosmic web, exactly. I like to think of it like a 3D spider web glistening with morning dew. The dewdrops are the galaxies, right?
That's a great way to visualize it. The galaxies form these dense, supermassive structures along the silk of the web.
But the focus of our data today isn't on those glowing drops of dew.
No, it's not on the filaments of matter at all. It's on the colossal gaps in between them, the giant pockets of empty air in the spider web.
Right.
In astrophysics, we call these cosmic voids, and I have to stress, these aren't just small gaps. They are unfathomably large expanses of absolute darkness.
The scale is staggering. I mean, we're talking about regions that are hundreds of millions of light years across, like the Buddhist void, for example.
The Buddhist void is huge.
It's nearly 330 million light years in diameter.
Yeah.
And when we say empty in this context, we mean extremely empty.
Or virtually no galaxies, no stars, no gas clouds, just nothing.
And for decades, astronomers treated these voids as essentially inert, didn't they?
Yeah.
Like they were just the passive, boring, black background that the interesting stuff just sort of sat on.
They did, yeah. It stems from a classical misconception about what space actually is. Because in a strictly Newtonian sense, we used to view space simply as a static container.
It's like a box.
Exactly, an empty stage where the actors, the stars and planets, performed. And if a region of that stage had no actors on it, well, it couldn't do anything.
It's just empty floorboards.
Right. It had no mass, therefore no gravity, therefore no influence on the rest of the universe.
Okay, let's unpack this, because how can nothing suddenly become a threat? I'm looking at these void measurements from the JWST data, and it seems to completely violate that basic Newtonian physics we all learn in high school.
It does, at least on the surface.
Right, because if there is zero mass inside these massive voids, there should be zero force exerted by them. So this aggressive push that astronomers are suddenly observing, it has to be coming from the geometry or like the intrinsic nature of the space itself, right?
That is the crucial leap. What's fascinating here is that modern cosmology, particularly following Einstein's general relativity, tells us that space is not a static box.
It's not just a container.
No, space is a dynamic, malleable fabric, and it has its own inherent properties. So when the JWST turned its instruments toward these massive voids, it wasn't trying to spot missing galaxies in the dark.
Which would be impossible anyway.
Exactly. It was actually looking at the behavior of the space itself. It used highly sensitive infrared sensors to measure distant light passing through these voids.
And this is where the mechanics of the observation get incredibly clever. Because obviously, you can't take a picture of nothing.
You really can't.
But you can observe how a void alters the light from background objects that sit behind it. The JWST is uniquely designed to capture infrared light.
Right, it's an infrared telescope.
But I want to make sure we're totally clear on the how here for everyone listening.
Mm-hmm.
How does looking at infrared wavelengths tell an astronomer that a totally empty void is actively expanding and acting like a cosmic pressure cooker?
Well, it all comes down to cosmological redshift and a phenomenon known as the integrated Sachs-Wolf effect.
Okay, lay that out for us.
Imagine a photon of light emitted by a very, very distant galaxy. To reach our telescope here on Earth, that photon has to travel across one of these massive voids.
So it enters the dark void.
Yes. And if the void were just a static, passive space, the photon would just cruise right through unchanged. But that's not what happens.
Because the space isn't static.
Right. As the photon traverses the void, the space inside the void is actively expanding.
So the photon is physically being stretched as the space it's traveling through stretches.
Precisely. The photon's wavelength actually gets stretched out as the fabric of space pulls it. And when a light wave is stretched, it shifts its color toward the red and infrared end of the electromagnetic spectrum.
Hence the term redshift.
Exactly. And because the JWST is the most advanced infrared observatory ever built, it can measure this extreme stretching with unprecedented precision.
And the data from that stretching was what shocked everyone.
Yes, what the data revealed is that the redshift isn't uniform. The expansion occurring inside these vast empty voids is happening at an accelerating, highly aggressive rate.
So it's not a gentle drift.
Not at all.
So instead of that overused analogy of a balloon inflating, let's think of the universe more like a loaf of bread rising in the oven.
I like that analogy.
Or maybe a massive block of sea foam. The voids are the air bubbles inside the dough. And what the JWST is seeing is that these specific bubbles are swelling up so aggressively that they are compressing the dough around them.
Yes, they are actively pushing against the matter.
They're actively pushing the galaxy filaments away, stretching the cosmic web until it's ready to snap.
That is a highly accurate way to visualize it. The empty space is exerting a repulsive force. It is literally devouring the fabric of space-time and tearing the structural integrity of the cosmos apart.
But that forces us to look at the inevitable consequence of this accelerating expansion. And the models in our source point to a deeply unsettling future.
Unsettling is an understatement.
Right. Now, the text mentions two distinct apocalyptic scenarios stemming from this void expansion: the big freeze and vacuum decay. And I want to make sure we don't conflate these two because the physics behind them are radically different.
Extremely different. Let's start with the more immediate consequence of these pressure cooker voids, which is the big freeze.
Okay.
This is driven purely by the macroscopic expansion of space. As these dark voids grow larger and larger at an accelerating rate, the distance between the filaments of the cosmic web increases.
So the galaxies are getting shoved further apart.
Right, and eventually they isolate galaxies completely from one another.
Here's where it gets really interesting, or perhaps terrifying. Because of this accelerating isolation, there will come a point in the far future where Earth's night sky will go completely pitch black.
Complete darkness.
And we need to explain why that happens, because it's not just that the galaxies are drifting far away and getting too dim to see with the naked eye. They are actually crossing a physical boundary called the cosmological horizon.
Right. It's crucial to understand a key rule of relativity here. While nothing within space can travel faster than the speed of light.
Right, that's the universal speed limit.
Yes, but there is no such speed limit on the expansion of space itself.
Space itself can expand faster than light.
Exactly. Because the expansion of these voids is accelerating, the space between the Milky Way and other galaxies is eventually going to be expanding faster than light can travel through it.
It's like trying to run against the flow of a treadmill that's moving faster than your top sprinting speed.
That's a perfect way to put it.
It doesn't matter how fast you run, you are physically being carried backward.
Well,
So the light emitted by those neighboring galaxies will eventually be entirely overwhelmed by the expanding space.
the photons will just never reach us.
They will be pushed beyond our horizon of sight. The Milky Way will be left entirely alone in an ocean of expanding nothingness.
Just a single galaxy floating in the dark.
That is the big freeze. A slow thermal death of the universe where everything becomes isolated, cold, and dark.
Which is grim enough on its own.
Right.
But then the source also brings up vacuum decay as a potential consequence of these expanding voids.
And this is a totally different beast.
Very different.
This isn't about galaxies drifting apart. This is quantum mechanics. This is about the very fundamental laws of physics collapsing, right?
Yes. Vacuum decay deals with quantum fields, specifically the Higgs field, which is what gives elementary particles their mass.
Okay, the Higgs field.
In physics, a vacuum is defined as a state of lowest possible energy. But there is a theory that our universe might currently exist in a false vacuum.
A false vacuum.
Meaning it's stable right now, but it isn't actually at the absolute lowest possible energy state.
Oh, like a boulder sitting in a small divot halfway down a mountain.
Yes, exactly.
It's stable for now, sitting in that little dent.
Yeah.
But if it gets pushed over the edge of that divot, it's going to roll all the way down to the bottom of the valley, which would be the true vacuum.
Exactly. And the concern is that the extreme stretching and aggressive expansion of space inside these immense voids could create quantum fluctuations.
Like an earthquake shaking the mountain.
Right. If the space is stretched enough, it could potentially trigger a tunneling event where the Higgs field drops into the true vacuum state.
The boulder rolls down the hill.
Yes.
And if that happens, a bubble of true vacuum would form in the center of one of these voids and just expand outward at the exact speed of light.
Which means we wouldn't see it coming.
Right. Because it's expanding at light speed, the information of its arrival arrives at the exact same time as the destruction. It would just instantly rewrite the laws of physics.
It would change the mass of electrons and quarks.
And essentially disintegrate all atomic structure as it passed over us.
It would be the instantaneous erasure of reality as we know it.
Just casual Tuesday cosmology stuff.
Just a little light reading.
Right. But whether we are facing the slow isolation of the Big Freeze or the sudden quantum collapse of vacuum decay, it all circles back to the exact same driver.
The expanding voids.
The voids are expanding because of an invisible force. And this raises an important question, which our sources dive deeply into. What actually is this dark energy?
Right.
Because we can measure its effects on the redshifted light with the JWST, but we still have to figure out the root cause.
This is arguably the greatest unresolved problem in modern physics. What is actually pulling the strings here? The research highlights two major hypotheses that physicists are currently grappling with to explain the mechanics of dark energy.
So what does this all mean for our understanding of physics? Let's break these two hypotheses down. The first one is the standard model assumption, right? The dark energy is just a natural intrinsic property of space itself.
Yes, Albert Einstein originally referred to it as the cosmological constant.
The cosmological constant.
The idea is that empty space just inherently has a vacuum energy baked into it.
So just by existing, space has this outward pressure.
Correct. Under this hypothesis, as space expands, it creates more space, which means it creates more vacuum energy, which pushes outward even harder, creating this infinite snowball effect of acceleration.
But there's a massive mathematical problem with that hypothesis, isn't there?
A huge one.
Because the vacuum energy calculated by quantum mechanics is something like 10 to the power of 120 times larger than the dark energy we actually observe pushing these voids apart.
Yes. It's been called the worst theoretical prediction in the history of physics.
10 to the 120 is an unimaginably huge error.
It is. The math just doesn't align with reality. The discrepancy between the theoretical vacuum energy and the observed cosmological constant is a glaring red flag that our standard model is incomplete.
Which forces cosmologists to look for answers outside of our standard physical framework.
Right. And that leads directly to the second hypothesis, which involves extra dimensions and brain cosmology.
And this is where the science feels completely indistinguishable from science fiction. Because the second hypothesis proposes that this accelerating expansion isn't an inherent property of our space at all, but rather a sign that our universe is being pulled apart by the gravitational force of a massive parallel universe.
It sounds radical, definitely. But mathematically, it solves a lot of problems. If we connect this to the bigger picture of string theory and higher dimensional physics, our observable universe might be a three-dimensional surface, a brane.
Short for membrane.
Right, floating inside a higher dimensional space called the bulk.
Okay, so let's make this visual. Imagine our universe is a sheet of paper floating inside a massive room. The room is the bulk.
Good analogy.
We are trapped on the 2D surface of the paper. We can't see the rest of the room, but, and this is the key mechanism in this theory, gravity might not be trapped on the paper with us, right?
Exactly. In string theory, most particles, like photons of light, are open-ended strings. They are firmly anchored to our brane.
They're stuck to the paper.
Yes, they can't leave. But the hypothetical particle of gravity, the graviton, is a closed loop.
A closed loop.
Because it has no open ends to anchor it down, Gravity can theoretically leak off of our brain into the bulk.
Oh, wow.
Or conversely, gravity from another brain, a parallel universe, can leak into ours.
So the dark energy inside these voids isn't an internal push, it's an external pull.
Exactly.
There's a massive parallel universe hovering just fractions of a millimeter away from our reality in a higher dimension.
In the bulk.
Right. And its gravity is leaking into our universe, grabbing the most fragile, empty parts of our space-time, which are these cosmic voids, and aggressively ripping our cosmic web apart from the outside in.
It really redefines everything we know. If this gravitational leakage is occurring, then the boundary of our universe isn't a closed wall. It's highly porous.
It's permeable.
Yes. And when the James Webb Space Telescope peers deep into these expanding voids, it isn't just looking at empty space. It is looking directly into a dimensional rift.
We are observing the gravitational ghost of a neighboring universe dragging our galaxies into the dark.
It is a staggering thought.
It really is. It completely recontextualizes the nature of reality. Because whether this expansion is driven by a snowballing cosmological constant within our own universe, or this dimensional tug-of-war with a parallel one in the bulk, the observable result is identical.
The outcome is the same.
The geometric structure of our cosmos is impermanent. The giant deserts of darkness are winning.
It's a sobering realization, but it's an incredibly vital one for our understanding of physics. We simply cannot fully comprehend the forces that govern reality by only studying the matter that is brightly lit.
Right.
The truest nature of the universe is written in the shadows.
Well, let's take a breath and recap the incredible journey we've gone on in today's deep dive. We started with the familiar structure geometry of the cosmic web, the giant glowing filaments of galaxies.
The morning dew.
Right. Then we shifted our focus to the massive, hundreds of millions of light-years wide voids in between them. We explored how the JWST used infrared redshift data to reveal that these voids are not just passive backgrounds, but rather active, aggressive pressure cookers expanding at an accelerating rate.
We then explored the dire consequences of this expansion, the eventual isolation of the big freeze as galaxies are pushed past our cosmological horizon, or the more abrupt, catastrophic threat of vacuum decay triggered by the extreme stretching of space.
And finally, we confronted the root cause of this acceleration, questioning whether it is an inherent flawed vacuum energy within our own spacetime, or the invisible gravitational pull of a parallel universe interacting with our reality through higher dimensions.
It's a vast amount of complex physics to process, I know, but synthesizing these concepts is really how we move our understanding forward.
Absolutely. And to you listening, I want to bridge the gap between these massive cosmological scales and your own daily life. Because everything we've just discussed, every single time you step outside on a clear night, look up and see the faint glow of a distant star or a neighboring galaxy, you're experiencing a deeply privileged, temporary window in cosmic history.
It's completely finite.
That starlight is a finite resource. It is a view that future inhabitants of the Milky Way simply will not have, because the voids are actively swallowing the horizon.
It is a truly unique time to be an observer. We are lucky to exist in an epoch where the cosmic web is still intact enough to be mapped and understood.
We really are. But I want to leave you with one final lingering thought to mull over, something that builds directly on this concept of the cosmological horizon of sight.
Okay.
We know that the universe has been expanding for about 13.8 billion years, and we just learned that as space expands, galaxies are actively being pushed beyond our visual horizon, completely disappearing from view forever.
That's right. The stretching of the voids has been ongoing since the very early stages of the cosmos.
So if this erasing process has been happening for billions of years, is it possible that our night sky is already vastly emptier today than it was when the Earth was first formed 4.5 billion years ago?
Oh, wow.
As you look up tonight, try to imagine how many magnificent glowing galaxies have we already lost to the void? How much of the universe's history has already been pulled beyond our reach, never to be seen again?
It's a haunting question. It forces us to wonder how much of the original cosmic web has already snapped, leaving no trace behind for us to find.
Something to think about the next time you look up at the stars. Thank you so much for joining us on this custom-tailored deep dive into the expanding voids and the dark mechanics of our cosmos. We hope this exploration gave you exactly the mind-bending aha moment you were looking for. Until our next exploration of your sources, keep your eyes on the sky and never stop questioning what lies in the shadows.